Hello and welcome to lecture 39 of the course Computational Complexity. Right. So in this lecture we will see Turing machines that take advice, what are they and how they are related to some of the circuit models that we have seen so far. So hopefully this will help address some questions that we have seen throughout the circuit complexity part. So one question that some of you may have been wondering is, like, we have always been calling this class P by poly. What is the reason for this notation P slash poly, right? And another thing that we have noted is that non-uniformity is such a big it has so much power, right? It is the non-uniformity, meaning the capability to have different circuits for different input sizes that can do a lot of things, right? So that can even allow P by poly to decide undecidable languages, right? So non-uniformity is like it's like a big game changer. So now, is there a way to kind of restrain the power of non-uniformity? Is there a way to control its power, right? This is another question that some of you may have wondered, right? Is non-uniform circuits, is that the correct model, or is there a better model for circuits, right? So there happens to be a better model called uniform circuit families, right? So a set of circuits is called a uniform circuit family if there is a function that can be computed by a certain computational power. So that function describing the circuits, okay? So that function should take as input a unary representation of the input length. So if for length 10 to obtain length 10 circuits, the function should take as input 1 2 3 4 5 6 7 8 9 10, an input of 10 ones, right? And output the description of the circuit family for, or output the description of the circuit that will take 10 long inputs, right? So this is the requirement, and this function should be computed in a certain computational power. So if you say P uniform circuit family, this function should be computed in polynomial time. If you say log space uniform circuit family, right? So this function should be computed in log space, right? So this could be log space P or whatever, right? It could be some other classes too. So this is what is meant by uniform circuit family. So I am just writing star uniform, and where star can be replaced with any bounded computational power class like P or log space or something else, right? And it should take as input a unary representation of the input length and output the description of the circuit. So any circuit can be described by saying how many gates are there, what are the gate types, where do the inputs come from, and so on, right? So basically implicitly describing the graph. So this is what is called uniform circuit families. So now uniform circuit families means that there should be a way to generate the circuits of each input length using some kind of an algorithm or some kind of a computational power, right? Some kind of an algorithm, and this will restrain the power of the this will kind of reduce the power of the circuits, meaning it will remove the non-uniformity, because again by the name itself indicates that these are called uniform. So this does not have the non-uniformity, right? Because you have a way to generate, given any input length, you have a way to generate a circuit family in an algorithmic manner, in a controlled power, using a controlled algorithmic power, and then now it is just about the circuit evaluating a certain input, right? So for instance, if you have a P uniform circuit family, so for first think of P uniform P by poly, okay? So you have polynomial sized circuits that are generated by a P uniform function, meaning if there is a function that takes as input the length of the input of the circuits and generate the circuit description, right? And suppose the circuit description is polynomial in size, so it will be a P uniform P by poly, and this happens to be equal to P. Why is that? We have already seen that P is contained in P by poly, right? So that still holds even if it is P uniform P by poly. And now to show the other way containment, you could use a polynomial time machine to generate the input description and also to evaluate the circuits, right? So P is equal to P uniform P by poly. In fact, we can skip the mentioning, can be omitted. This mention can be omitted because any circuit family that can be described or generated in polynomial time, right, that will necessarily be of polynomial size, because in polynomial time we cannot hope to output an exponential size circuit. So if you just say P uniform circuit family, that itself has to be equal in power to, or like the class of P uniform circuit families must be equivalent in power to P. Similarly, you can also verify that log space uniform circuit family, even that is equivalent in power to P. The class of languages that are decided by log space uniform circuit families is equivalent to the class of polynomial time algorithms. If you again look at the proof of the Cook-Levin theorem, the circuit family that we obtain is actually a log space uniform circuit family. So that is another thing to note. So P is actually equal to P uniform circuit family as well as log space uniform circuit family. So we may mention P log space uniform P by poly, but that is not really required, because again, if something is generated in logarithmic space, excuse me, then it must necessarily have polynomial size. It cannot have more than polynomial size, right? So you can try to work out the above two. I am not getting into the details, but it is rather straightforward. Okay, now let us define Turing machines that take advice. So what are Turing machines that take advice? So we will denote them as d time Tn/an, and this is the genesis of the notation P by poly. Okay. So the class of languages, so these are d time Tn/an. These are Turing machines that take advice. What are they? These are the d time Tn/an is the class of languages that is accepted by a d time Tn Turing machine, which has an advice string available to it. The advice string is an. Okay. So to be more formal, L is in d time Tn an if there is a deterministic Turing machine M that runs in d time Tn, or that runs in time Tn, and it gets as input, in addition to the actual input, it gets an alpha n string as input, okay, where alpha n is of length at most ai. Okay, so this is a typo, this should be an, right, and where an is some function, it could be polynomial, exponential, logarithmic, whatever, right. So the alpha n is the advice string, and that the length of the advice string should not be more than an. Right. So this is the definition of a Turing machine that takes advice. So this may seem similar to the NP definition of NP, where it had access to the verifier model of NP, right, where we had a proof string or witness string or certificate string for each input. The main difference here is that, so there are two differences. There, the length of the advice string, or sorry, not advice, the witness or certificate string was polynomial, bounded by a polynomial in the input of the in the length of the input. Here, the length of the advice string is bounded by some function an. This could be anything. It could be logarithmic, it could be polynomial, it could be exponential, some function an, right. It could define, it just changes the parameter in the definition. Second thing, rather this is the more important point, is that there the certificate could change with the input, right. For each input we could have a different certificate. For each graph I could have a different 3 coloring. For each Boolean formula I could have a different satisfying assignment. Whereas here there is still some variation with input, but the advice string alpha n, okay, so alpha n, this is fixed. So I'll use a different color. This is fixed for each input length. So once an input of length n is given, the alpha n is fixed, right? There we did not have that. Where we could have a separate witness or certificate string for each input. Even two different inputs of the same length could have different certificate strings. Whereas here the advice string is just dependent on the length of the input. It cannot keep changing based on the input. So for a fixed length, whatever may be the input, the advice string has to be the same. It can only be dependent on the input length. Okay. So the alpha n is fixed for a specific n. Right. So these are the main differences. The second difference is rather more important. Right. So we cannot, it does not have as much power, or it does not have the kind of power that NP has, right, because it is fixed for a certain input size, and X is in the language if the Turing machine accepts it along with the help of the advice string. So the Turing machine should accept X and along with the alpha of the corresponding input length. So just to give some idea, we saw U halt, right, which is the unary version of the halting problem. This actually was in p/1. The advice string here was just a 1 bit of advice string, right. So for each input length we needed to know whether that input length k is in the language or not. So the advice string could be 1 bit. We could say 0 when the input length is input that there is no string of length k in the language, right, and you could say 1 when there is only one string, that is 1 power k, that is in the language. So U halt is actually in p/1. In fact, it is actually it's in p/1, but you could, if there is a class of smaller size than p, then we could have that as well. And p by poly, okay, p by poly, what we have already seen, is actually equal to d time n power c divided by n power d, okay, or d time n power c / n power d. So now you could see why the notation p by poly has is used, because the numerator, or the sort of numerator that we have is d time n power c, which is, if you take the union of over all the c, it is just the class p, right, d time n power c, and the denominator is n power d, which is again a polynomial. So that's why we call it p by poly. This is the genesis of the word p by poly. So let us see why this is the case. So the claim is that p by poly is the class of all languages that are decided by polynomial size circuits. And now I am saying that this is the same as the class of all languages decided by Turing machines that take a certain amount, a polynomial length advice. So let us see why that is the case. Suppose L is in p by poly, okay, which means there is a polynomial size circuit family that decides L, right. Now why is it in d time, okay, so why is it in d time n power c / n power d? Now, so which means that given an input that the Turing machine has to decide, right. So what will the Turing machine do? The Turing machine could notice that the Turing machine has to be same for the entire language, but it could use an advice string, right, or the advice string could vary based on the input length. So the very obvious or kind of immediate thing to guess will be the description of the Turing machine, description of the circuit. So for each input length there is a different circuit, So this n power d could describe the circuit for length n. So for a certain length input, n power d, the polynomial size input string could describe the circuit for length n, and then the deterministic Turing machine merely simulates the input or evaluates the circuit on that input, right. So simulates or maybe evaluates is a better word, maybe evaluates the circuit at the input, right. So this is why p by poly is contained in d time n power c slash n power d. Now let us see the other direction. Suppose there is a Turing machine that takes advice, or suppose L is in a Turing machine that takes advice. Okay. Now L is in d time n power c slash n power d. Right? So this means there is a Turing machine that takes x as input, and for each input length it has a different advice string, and where the length of the advice string is bounded by a polynomial. So length of alpha x, which is the advice on the input x, is upper bounded by n power d. So it is alpha x is the length of the input, right? So I should actually say the length of alpha x, which is length of alpha n, is upper bounded by n power d. Now we could recall again, once again recall the proof of Cook-Levin theorem, right? So there is a Turing machine that runs in polynomial time, right? D time n power c, that takes input x and that takes a certain alpha n, right? And we could build a circuit that evaluates that corresponds to the decision process of this Turing machine, right? So that circuit will that circuit will take x and alpha x or alpha n as inputs, but then alpha n is fixed for a certain input length. So we could as well hard code the description of alpha n, or hard code the alpha n into that circuit, so that may possibly simplify the circuit, right? So we can build a circuit for this as in by the proof of Cook-Levin theorem, right? So this is by proof of Cook-Levin theorem. So we are really milking the proof of Cook-Levin theorem again and again by noticing that there is the computation is local, so you could replace it with a constant size circuit, and so overall it's a polynomial size circuit, right? So you could build a circuit and then you hard code alpha n into that circuit, and then that's it. You have the circuit that decides whether if x is in the language or not, and obviously that circuit will be polynomial sized. So that is why d time n power c slash n power d is contained in p by poly, and that is all that I have to say in this lecture. Right. So we saw what are uniform circuit families. It could be any uniform, p uniform, log space uniform, and then we saw the definition of Turing machines that take advice. These are Turing machines that run in time Tn, but has access to an advice string of length an, okay, of length at most an, and this advice string only is a function of the input length, not the input itself, right? And it could vary with the input length, but will be same once the input length is fixed. And then we saw that p by poly is in fact d time n power c slash n power d, union of overall the c and d, right? And that's all I have for this lecture.